Hi, I'm Dan Winter, working with Roger here, and Paul Harris is with us, with Bill Donovan. And all of these projects are around the concept of the fractal field, and we now know how dramatically fractal hydrogen is, and that's why it's so potentially negentropic, and under certain conditions, everyone knows that hydrogen gas has unique and wonderful properties, from Brown's gas to Joe cell, all these Santilli's magnet gas. Lots of people have names for this. But the bottom line is hydrogen gets magic and syrupy and centripetal and a real significant source of energy. And everyone you ask agrees that hydrogen is probably the best energy source of the future. So here what we're looking at is, in the Atomic Hydrogen Catalyzed project, is specifically a process whereby there is an arc. And the arc, as the hydrogen passes through it, of course, splits the hydrogen from the molecular to the atomic. And then it hits a very particular metallic catalyst. And this process has been known in history, but in our case, we're in an excellent position to make new use of efficiency here for various reasons, as Bill mentioned, direct coupling to the Tesla turbine. Also, as in the original Melbourne project, I wrote a new series of equations which not only predicted the radii of hydrogen, they are simply log functions of golden ratio times Planck length, which proved that hydrogen's radii were phase conjugate and fractal, predicting also, interestingly, photosynthesis frequencies. So that new set of frequencies for conjugation and harnessing centripetal forces allows us to make more efficient use of the electric arc and field to split the molecular to the atomic hydrogen. The example we used in the Melbourne project was Canzias's work, where in fact my new equation for hydrogen Planck length and time times exponent's golden ratio predicted exactly the RF frequency that Canzias used. You all remember the famous YouTube films. It's a little bit of radio waves is hitting this cool glass of water, and they light the match and the water burns in the presence of the right longitudinal. Well, that was an introduction to the concept that with the right arc, the right harmonic content in a charge field, the splitting of water, of course, becomes more efficient. And here we're applying that, and it's to a new understanding of how to split hydrogen into atomic from molecular. Now, many people aren't aware, but to just sort of explain what Bill was just mentioning, aren't aware of the difference between molecular versus atomic hydrogen. But essentially what Bill is saying is, you see, hydrogen never travels as an atom, a self-atom. When hydrogen is hanging out, it's always hanging out in pairs, basically. Mm-hmm. And what Bill mentioned is a very dramatic insight. This is something physicists should scratch their heads and study very carefully. What Bill just said is that the energy to split the pair of hydrogen atoms from a molecule into separate atoms of hydrogen, the energy to split that, is something on the order of 1/10 to 1/100th of the energy that comes back when they recombine. Now, hello, Mr. Physicists out there, but we suggest you strongly study the physics here, because there's lots of evidence in the equations, and we're going to provide links and references and physics, and this is all part of the due diligence here. And you can see what Bill was explaining. When Bill said 25 to 100 COP, and that means coefficient of performance, that means 25 to 100, just with very conservative calculations of the amount of energy that comes out that versus what goes in to simply split and recombine the hydrogen with a catalyst. So it sounds almost too good to be true, but it isn't. It's deep and solid and powerful physics and available for commercial harvest, and that's why we're here, and we invite you to do due diligence like we have. The cool thing is that we have a great team here to put this together. Speaking of which, our hands-on person here is Paul Harris, who has amazing background in these areas. He's our hands-on plasma guy, high frequencies, all kinds of cool stuff. Paul's very capable. Here's Paul Harris.
Thanks, Dan. Yeah, basically everybody's heard a lot about what's going on these days, and you hear all these buzzwords like hydrogen economy, and everybody's studying hydrogen and know that it's the fuel source of the future. But what nobody's looking at, everybody's thinking about using hydrogen in a fuel sense and running it through a combustion engine, or using it in hydrogen fuel cells, create electricity for transportation. But nobody's really gone back and looked at the history of what's gone on. And Irving Langmuir is just a really interesting guy. And I know both Bill and I have collected a lot of old chemistry and electronics books.
Sure, yeah.
And Irving Langmuir from 1909 to 1950 worked at General Electric. He actually got a Nobel Prize in chemistry in 1932, and he's the one who coined the word plasma, that he got from realizing almost a relationship to blood plasma, and how atoms moved around in this glowing state. So what we're re-looking at where pieces are missed, because in the modern textbooks, everybody's kind of been following everything that's written in the textbooks. That's all they know, that's what they've been taught, and that's what they're sticking to. But there's many holes in the puzzle here that haven't been addressed throughout modern times ever since then. So we're going back and looking at the fundamentals of the plasma chemistry, and have found a lot of unique new discoveries that really have been left out of the history books. So here's Bill to give a little bit more information on that.
Okay. Thanks, Paul. And anyway, so essentially what we're looking at with the Langmuir process is that we're splitting the hydrogen molecule apart, H2 to H1, and there is a possibility that in the presence of a metal catalyst that this can produce neutrogenesis, or neutron formation, and deuterium formation. This is typically on the order of 55 megawatts per gram, to give you an idea what the amount is. Huge. And this would be, again, about 1,000 calories per mole gram on the input side to begin the process, and this would result in around 100,000 calories per mole gram out, with an overall COP of about 100. So with an extraction, or with a conversion efficiency of 50%, we're looking at a net COP of 50. And so, I mean, we would be absolutely delighted if that would happen. Of course, we're going to be assuming this on the low end to begin with. And this means that our efficiencies will surpass any efficiency that anyone previously had. And we're quite enthusiastic about this, and the possibility of producing heating, which is far more efficient than anyone has at the moment, and direct plasma, which can be converted directly into electricity, proprietary coating on a Tesla turbine, which can produce direct output, and for mechanical output to an alternator, and as well as the use of quantum well antennas, which will produce direct thermal output, which of course obviates the use of a Tesla turbine. These devices are typically around 80 to 95% efficient. So again, our COP would be, getting way up there. So we're looking at a very modest investment as far as getting this project off the ground, and we're also, I mean, it's very low, but the rate of return is quite high. The plasma is so versatile that it could be used for practically anything from lighting to zone heating to for electrical generation as well. And this is a system whereby molecular hydrogen is split into its atomic form and then allowed to recombine in the presence of a metallic catalyst. The energy which is supposed to be put out, it takes about 1,000 moles, rather 1,000 calories per mole gram to split the hydrogen, and it has been estimated that it would produce 100,000 calories per mole gram on the output side, and which would result in a thermal COP of 100. If you have an efficiency or an anticipated efficiency of at very least 25%. This would knock the net COP down to 25, which is still far higher than any commercial catalyzed project that's out there right now. This would be with Leonardo Corporation or with Defcalion. We're anticipating a large return, and we're also anticipating that with the difference in our process, which means that instead of using just a thermal output, we are using a direct energy conversion system using a Tesla turbine, using a proprietary coating on the turbine. This will eliminate hot spots, increase efficiencies. Typically, Tesla turbines with a hollow shaft have 85 to 90% efficiency, 60% without, and using a conventional alternator, this knocks it down to around 50% overall efficiency. Mm-hmm. Now, we're, of course, lowballing it with the overall COP of 25, but we're anticipating somewhat much higher. It's best to anticipate something lower, and of course, if you're higher, then everything is just a delightful outcome. So that's the overall part of this.
So basically, for a modest investment in a lot of the equipment that we need, we actually have quite a well-equipped laboratory here in France as well as Canada. And what we are looking at doing is just getting a few more pieces of equipment for the actual characterization of these hydrogen reactions. And the next step in the process is what we want to be sure is that we understand the scientific principles fully before we proceed with the actual applications of these things, because what that's going to do is give us a really strong foundation to develop a multitude of applications across the board, that this is going to revolutionize really energy technology and the history of mankind. So here's Bill with a little bit more.
Okay, as far as the equipment goes, we're looking at probably a high current power supply, tungsten electrodes. We have simplified the initial experiment down to just one tube for the initial calorimetry experiment with the help of Jean-Paul Barberian. And this tube will let us know if thermally we are on track with our thermal COP of 100. The tube will be purged with argon gas and then filled with hydrogen, and we'll use various pressures to determine what the proper operating pressure is. And after that, then it will be immersed in a bath of liquid, water probably, and then we'll be doing the calorimetry test directly with that. And since it's going to be a sealed unit, there won't be any problems with any kind of flow-through, which is usually a nightmare to begin with. So that eliminates that major problem. And as far as other equipment goes, we're going to be using a welder for a power supply, probably a full-wave bridge rectifier, high current. Having the unit completely sealed allows us to take samples of the gas before and after, and we can see if there's any deuterium formation in the vessel, which is a very important point, because if deuterium formation is actually showing up, that means that we are actually producing a type of transmutation which is very well known astrophysically. I mean, astrophysicists have plotted deuterium, tritium, helium formation, and we know how much energy this produces. So what is produced on the stars can also be produced here. It's just a matter of how it's done. On the stellar basis, we know the carbon cycle is in use in some stars catalytically, which produces both deuterium and helium. And we know that certain M-type dwarf stars will burn hydrogen into deuterium in a half reaction. This is primarily what we will be doing. The other equipment that we have is very low cost, and we anticipate, as far as a dollar value, to probably be below $10,000 for the cost of the original.
Right, yeah, so basically what Bill's saying is, with a very small amount of equipment for our initial investigations here, we'll have a very high value set of data that's going to quantify these results, and as well as being able to show to the whole cold fusion community, who's really gained a lot of credibility in these last few years in the whole renewal of this whole cold fusion concept. And we'll have some very interesting results for the future of the cold fusion science as well.
So in summary, the hardware steps in this process, proof of concept, which is a dramatic concept that you have 50 to 100 times more energy than out than in, when you split hydrogen from a hydrogen molecule to atoms and then allow it to recombine with a catalyst. That's the core here. The concept is clear from history, Lang, Muir, and others. The ability to do it commercially in efficiency has been limited only by this real new understanding of the fractal structure of hydrogen. So the benchmarks here would include that we show the efficient arc, either AC or DC, that would then split the molecule hydrogen efficiently, and then show the distance and the plasma and the spacing of the placement of the catalyst metals. Some of the catalyst metals, there's about 3 involved here, are quote-unquote precious metals or semi-precious, but they're not that expensive. And the good news is they're pretty hardy. They can handle this. And so, and there's many ways to do that, including in conjunction with the Tesla turbine, which is proprietary and very exciting here. And so some of the benchmarks here is making the arc, getting the split, and then showing the recombine, and then quantifying the energy gain. And we have 2 ways in mind to quantify the energy gain. Working with us is Jean-Paul Biberian, who is Europe's leading fusion physicist, and he is working with us closely on this and offered and to be greatly involved, including with the calorimetry, which is his specialty. The calorimetry means simply that you measure the ratio of output heat to input power to quantify in watts. Whether it's heat or electricity doesn't matter. That's the net energy gain. So the sequence of steps is very straightforward here, and we can begin rather promptly, and the investment is very modest.